Hey everyone, thanks for joining me here in today's session. This is introducing container image support for AWS Lambda SVS 209 as part of AWS reInvent 2020, the second part of it, which is currently happening right now in January 2021. My name is Chris Bunce. I am currently the lead of developer advocacy for serverless at AWS. I have been at AWS for a little over 8.5 years now, across a number of different roles, but spent the last 4 years focused on this space of serverless. You might have seen mine or my team's talks at reInvent this year, or seen this in tech talks, or read our blog posts, or seen stuff that we've published on a site that we have called Serverless Land. But we're here to help educate, inform, teach, enable, and in general just help people build serverless applications to the best of their ability. So why are we here today? Well, at reInvent 2020, back in December, we announced a really awesome capability for AWS Lambda, which is a compute service. For those of you who are new to AWS Lambda, it's a service that we first announced 6 years ago, back in 2014 at AWS reInvent. And since then, it's grown to become an incredibly popular service with our customers. We see companies doing all sorts of unique things, building all sorts of unique applications with Lambda. Now, our focus will be almost entirely on Lambda today. This is a 200 level course, so we will not be going super deep. Hopefully, though, I'll give you just enough bits of information so that you can feel excited and interested and know how to take the next steps into using this new capability. So again, what are we talking about here today? We are introducing container image support for AWS Lambda, or I should say we just did recently, again, back in technically December 1st, as part of Andy Jassy's keynote, the CEO of AWS. Again, this is a big topic. There's a lot that we could go into, but if you've been following along reInvent so far, sessions are a little shorter this year. So we only have 30 minutes. Again, because of that, I can only get into so much. So again, my goals for this session for you today are for you to understand this feature, understand why we built it, understand a little bit more about how to use it, understand some aspects of what makes it different versus what maybe doesn't change as part of this. And we'll talk about some of the related services and nuances and capabilities again along the way. But again, thank you for joining me here for this session. So let's get started. Again, we just announced container image support. Why did we do this? There's a number of different reasons as we'll go into here today. One of the key ones is better dependency management. Talk a little bit more about this here in a moment. Also, going along with this, as you'll see, it'll allow you to use some of the tools that you've been using so far if you've been building container-based applications, or in the future, if you might be building container-based applications, now you can share that same tooling with your Lambda-based infrastructure as well. And going along with this capability, we also announced kind of a sibling feature, I should say, which is a change to Unlimit, which now with the container image support functions, you can launch functions up to 10 gigabytes of application artifact. We'll talk about how that's useful here in a moment as well. Again, diving a little deeper into this, some of the challenges that we have seen customers have with Lambda, and again, I've been directly in the Lambda organization product team for the last 4 years. However, I've been with AWS since we first announced it. And one of the common challenges that customers have found has come around managing the lifecycle of a Lambda function, as well as managing how they install software into the Lambda environment. For those of you that might be newer to Lambda, essentially Lambda at the end of the day is allow you to run your code on top of a completely managed infrastructure, a completely managed service. But that, however, does live on top of servers. So yes, the servers that exist in serverless that you don't have to deal with are there. Now your Lambda function runs inside of a Linux environment, in this case Amazon Linux, which is our own distribution of the Linux operating system. And we have runtimes that run in what's just called Amazon Linux, or the first kind of version of Amazon Linux, as well as runtimes that run in Amazon Linux 2, which is a more recent, long-time supported operating system. Now, when it comes to installing packages, there are obviously the native packages that you might be familiar with in an operating system. So if you've ever managed Linux-based hosts before, you've used tools to install operating system-based packages. These could be everything from low-level code libraries to full applications to server applications and things like that. With Lambda, it hasn't really been super easy in the past, I should say, to be able to do that. We have had capabilities and ways that you could bring in those software packages in with your application artifact, but it was never necessarily a really trivial thing to do. Similarly, we've seen customers who want to use the dependency systems and package types for their runtime. So for the language you're building your application in. So for Node.js, this is things like npm packages. For Python, it could be pip packages. For Java, there's Maven. For C, for .NET, there's NuGet, and so on and so forth. Ruby has gems and things like that. Now, you could always bundle those in using your normal build tools, but essentially then customers would have to manage those packages files or the requirements.txt or what have you for the different language. And again, previously, and still today, with the zip file support that we have in Lambda as a deployment artifact, you're limited up to 250 megabytes with zip files. So again, part of this is enabling you to have up to 10 gigabytes of storage to be able to deploy your application. This becomes really useful for customers that are doing things with machine learning frameworks and packages, customers that are using scientific libraries, and just in general, customers that want to do things like bundle in, say, various bits of training models for, say, machine learning, or again, all sorts of other places where 250 megabytes just wasn't enough. Examples of this are things like headless Chrome, or certain complicated data science libraries, again, like NumPy, SciPy, and things like that. So now this becomes possible, and it becomes easier because we support, as part of this, the ability for you to use a Dockerfile to configure your container image. And we'll talk about that here more in a moment. The last bit about this, though, is that because we're using a container image format, which is something that's familiar to container orchestration systems, then you can leverage tools that you might already be using for your container orchestration environments. And so these range from CI and CD tools to security tools to code analysis tools to all sorts of things that could exist in your developer workflow. So again, number of benefits for why it made sense to do this. Again, it doesn't change everything, and we'll talk about what stays the same here as well. One thing that's very, very, very barely changed is the developer workflow. So again, you're still deploying your Lambda functions as functions. That has not changed. The event model hasn't changed, and we'll talk more about that here in a moment. What has changed is that we now require that application artifact to first be stored in Amazon ECR, or Elastic Container Registry. And so when you create your container image, you upload that to ECR. You then configure your Lambda function to have your function source in ECR. And then when your function is invoked, the Lambda environment will pull that code down and then execute the function, invoke your handler and all of that, just like it always used to. Technically, when you configure the Lambda function, we actually pull down that image and cache it ourselves. And we have a couple different layers of cache that help us speed up the scale at which your Lambda function might be operating. Again, we want that to not have an impact on performance. And generally speaking, customers are finding that there really is no impact from the container image-based model versus the zip file model. Again, there could be some nuance if you have really, really large container images, but generally speaking, for the most part, I haven't seen any feedback that shows customers seeing really any difference as part of this. So that sounds pretty easy. Package a container, put it in ECR, configure your function, everything else stays the same. Let's get a little bit deeper into some of this. So as part of this launch, we have basically launched a container image per runtime. So this allows you to very easily just take your existing code that you have for Lambda, take the container image that is aligned with that runtime that you've programmed it for, and then be able to deploy your functions with that. We have also released container images for the runtime API. So the runtime API allows you to bring any language that you want to Lambda. Essentially, you could think of it as a bare bones environment that allows you to execute anything from Erlang to C++ to PHP to a number of different languages. And so you have both of those options that are available to you. We've made those images available both in Docker Hub and in ECR Public, which was just recently announced at reInvent 2020 as well. And so this means that you could pretty easily find these container images and then build off of them. Now, when it comes to talking about these container images, we follow specific manifest formats. So this is going to be the ones that you see listed here on this slide. So the Docker image manifest v2, schema 2, and then the OCI initiative spec v1 and up. So you could basically build your own containers from scratch if you want to, and they don't need to be Amazon Linux either. So you could use Linux distributions such as Alpine or Debian and package up your application, again, so long as it matches the formats for this. There are a couple other small aspects to this in terms of some environment variables that you have to pass into your function or configure inside of your Dockerfile. And all of that is right here in this link that you see at the bottom of this slide, which you could find in the Lambda documentation. So again, you can bring your own container formats, you can bring your own container images based on other distributions and be able to configure them as you need. So going back here real quick, I had something on this slide that may be very new to people who aren't familiar with the concepts behind container images, specifically this aspect here of a Dockerfile. What is this thing? So Dockerfile is essentially a configuration as code format file that allows you to describe how your Docker, or your container image, I should say, should end up looking as a result. We see here that this is a very, very bare bones example, of just 4 lines. What do these 4 lines do? The first one says that we're going to create an image based off of another one. So from, and then we're referencing a Node.js v12 base image that is an ECR public. That's essentially what that first line there means. The second line says copy and then a number of files into a specific directory. So assuming that I have written this Node.js code, I am going to ask that when I build this, it copies the code into that container image as well. We're then going to execute npm install. For those of you who know Node.js, you know that this is going to install my dependencies based on my packages .json file, which I'm including all of those into this image. And then when this image is actually run as a running container environment, I want it then to execute my handler. My handler is going to be the main entry point into the business logic of my code that I've written. Now, what you don't see here are a bunch of the bits that are from that top line there, that from container image referenced in ECR public. Again, some of what's in there is the magic that we pre-bake into our base container images. So there's a bunch of things that you don't have to do because we do that for you. And so again, Docker files are the way that you can configure this. Docker files are fairly powerful. There's a bunch of things that you can do in terms of installing packages, in terms of deciding how you want to basically include certain files from your operating system, include certain aspects of your code, instantiate things like environment variables as part of the build process. And so there's quite a lot that you can do with Dockerfile. In fact, we could probably almost have an entire session on what you can do with it. So I encourage you to check both the Lambda documentation that talks about what parts of Dockerfile we do support, and then refer to the Dockerfile documentation for understanding more about that. Now, there are 2 major components that go along with the container image support that we launched, the RIC and the RE. So the RIC is the Lambda runtime interface client, or clients, I should say. Now, what the RIC allows you to do is it allows your code that's been bundled into your container to be able to talk to the runtime API. And it does this via the runtime API, essentially interface client that we see here. All container image-based functions operate like a custom runtime function would inside of Lambda if you were packaging it up with just the zip format file. So typically you would have to have a bootstrap. That bootstrap would talk to the runtime API. In this case, we didn't want to make it that complicated. We want you to be able to take existing Lambda function code, package it as a container, and be able to run that without having to add a lot of bits or work for you. So in this case, the RIC ends up basically being that work. It is that bootstrap. It is that thing that shims between the API and your function handler, as it were, at the end of the day. Now, we've released these for each of the managed runtimes available in GitHub. So I've included the link here just for Node.js as an example. But you can go into the AWS GitHub organization and find this for the language that you might be running. Now, the second part of this is the RIE, or the Runtime Interface Emulator. This is a little different now. Now, what the Runtime Interface Emulator allows you to do is it supports the ability for you to test Lambda functions locally. Now, we've had the ability to do this with the AWS SAM CLI tool for a while, but this works similarly, but also a little bit differently. In this case, what this can do is it can run on a local interface for you, or it can run inside of another container on the same host where you're running your Lambda function container. And it allows you to basically translate an HTTP request into a JSON event that then the RIC can understand. So this mocks the runtime API for you. And again, this can be for testing purposes. This can be for mocking up, complex architectures, doing local development, and so forth. And so the RE here makes it really easy for you to be able to do that. It is included by default in our container images, and then you can also find the emulator as listed here in GitHub. Now, you typically won't be interfacing with the RE unless you're doing that local testing. And you'll typically only be touching the RIC or the runtime interface clients if you're building your own container images. However, if you are not building your own images, and if you are not doing local testing just directly via the ports, maybe you're still using the AWS SAM CLI, then this may not necessarily be that valuable to you. But you'll see both of them mentioned in the documentation for building container images, and it's important to be aware of them if you do end up building your own containers. Okay, so the build and deploy flow, again, doesn't change that much from what it used to look like in the past. The steps that you would have here is you would create your application. So write your code in your IDE of choice, whether it be anything from VS Code to Cloud9 to some of you that I know write code in Notepad or WordPad or VI or maybe something like Emacs. You write your code. And then again, for a container image-based deployment, you then have to have a Dockerfile or some sort of file that's going to help you build your container image to the required specifications so you can create and update that. You would then execute a Docker build or a similar build command that would create your container image for you. And again, this could vary depending on the tooling that you're using. What you would get from this is your container image. Typically then you could then test that. So you could use the RE, which we just talked about, to do a local test of your function. You could even deploy this up into a container orchestration system that you're running for further testing if you're not ready to, say, put it all the way up into the cloud, as it were. From here then, you would upload that container image to an ECR repository, and then you would configure and deploy your Lambda function. And again, that would happen with tools like SAM or CloudFormation or any of the number of tools that exist in the ecosystem today. On create and update, as I mentioned earlier, the Lambda service actually pulls down that image from the ECR repository on your behalf and stores it in a cache that the service itself runs. And again, this is to help speed up, minimize any impacts of cold starts, and make sure that that image is available so that we can use it going forward. Now, important to note, anytime that you change that image in the container registry, it is not going to automatically be updated by the Lambda service. You must point the Lambda service at whatever that version is that you want to configure it for. So this does mean that you can do repetitive kind of updates of an image. You can replace them, you can remove them, but up until you go and configure or update a Lambda function, it is not aware of what's inside of your ECR repository. So again, important caveat, it's not going to automatically update because you push it live. You do have to go and make that change to the Lambda function. Now, I mentioned AWS SAM CLI. This is a tool that we have that greatly simplifies building, deploying, and managing serverless applications. It has been updated to be able to support container images. And if you've used SAM before, you know that it really, really makes it easy for you to deploy serverless-based applications. Or I should say Lambda-based serverless applications. In this case, again, with the OCI support, it makes it really, really easy. And so what we've done, which is something that we've done in the past with SAM, is that the SAM deploy command wraps up a whole bunch of these steps for you. It will take care of taking your image, potentially creating an ECR repository for you, building your image, uploading it up to ECR, and then deploying that Lambda function on your behalf. And you can do that all with the SAM deploy command. It supports a guided functionality that allows you to answer a bunch of questions so that your function is deployed the way that you would like it to be. And it also supports the ability for you to create a new application that ends up being OCI based. So these are all updates that were just put into AWS SAM right towards the end of the re-event period back in December. So I definitely encourage you to check that out. Again, really powerful way to do this. SAM has a number of other capabilities to allow you to do local testing in a couple different ways. You can mock an API gateway, you can mock the Lambda service, And so it's pretty powerful by itself, but definitely check this out if you want to simplify the deployment of your container-based Lambda functions. Okay, so we've talked a little bit here about the developer workflow, a little bit about the OCI images. We've talked a little bit about some of the things that have changed. Let's talk about some of the things that haven't changed, because it's important to know what this means in basically, I guess, like the broadest sense. This is really just a kind of a quick list again here of what has changed and what hasn't changed. Again, what has changed, larger artifacts are now possible. So again, you can deploy applications up to 10 gigabytes. You do need the RIC, the RIC, the runtime interface client to talk to the runtime API. Again, that's built into the provided container images that Lambda has made available to you already. So you don't have to do this unless you're building your own. And then again, one thing that's very different here is because you now own that runtime, you own that container image, you will no longer get automatic updates to runtimes. Now, this is an important caveat towards how Lambda works as a service, and it's something that we, from the very early days of the service, have often talked about as being a key benefit, which is that we take ownership of that runtime so that you just consume it. There are, however, times for customers where that's not ideal. Specifically, if you have an application that maybe is very, very tied to specific releases of that runtime, maybe you have certain dependencies that you use that aren't going to be aren't forward compatible, and so if we update the runtime, that could maybe break your function. Those things have happened for customers. And the downside is that you have to now take the ownership of updating that. So when there are performance fixes, when there are security or bug fixes, and when new versions become available of runtimes, that's now on you as the developer to own updating these container images. So again, really important to understand that bit. It's a pretty big shift in terms of what I consider the contract that Lambda provides for you. What things don't change? I'm going to go a little deeper into each of these. The invoke model does not change. Storage options do not change. Logging metrics and things like AWS X-Ray and how you use them does not change. Other service limits don't change, so you are still limited to 15 minutes of maximum function duration. How Lambda scales in terms of in-region burst limits, your account limits doesn't change. That stuff all stays the same. And then billing, which I'll talk about the billing update that we've had here in re:Invent as well, also still functions exactly the same. So stepping back broadly, again, what hasn't changed is how Lambda itself works. You still create Lambda functions. Those functions still have to have all the same bits. So you still have to have a handler for your function that you tell your container to have the entry point to your code when an event comes in. That doesn't change. Handlers work the same. The responses out of your function execution still works the same. None of that changes. How your function gets events, again, does not change. Event structure doesn't change. The event object doesn't change from the invoke sources that come through. Again, the only thing that might change is that if you build your own container images, then you're having the runtime interface clients run alongside of your handler. And then lastly, the context object, or the information about your function execution, about your environment, doesn't change at all in terms of the bits that are related to how your function operates or executes. Another thing that doesn't change, again, is how Lambda is invoked. So Lambda is an event-driven compute service. What this means is that there is no direct port or socket that you connect to today that enables your function to be executed. If you're familiar with what I would say is a more service or server full model, then you're used to, port 80 or port 443 being available for a web service, and you would make a request with your web client, and it would execute the request inside of, say, Nginx or Apache or something like that. Lambda doesn't work that way. When you want to invoke a Lambda function, you talk to the Lambda API. The Lambda API then executes your function code on your behalf on a compute environment that is running your function code. Nothing about this has changed with the announcement of container images. It is still this event-driven model. There still is not a port or socket that you would have available to you. All of the different event services that AWS has, or I should say services that AWS has that can invoke Lambda, which is over 100 of today, still work exactly the same way. Okay, in terms of storage that's built into your function with Lambda, the same types are still available. So you have the memory that your function can be configured for. Now this has changed. I'll talk about this here more in a moment. We have increased the limit for memory for a Lambda function now up to 10 gigabytes itself. Again, this is different than the 10 gigabytes of artifact storage that you have. In terms of temp space, that is still at the previous limit of 512 megabytes. Nothing has changed with that inside of the Lambda environment as part of any of these announcements. And then again, the deployment package has changed. So now you have up to 10 gigabytes of storage in that deployment package. So you can include all of the libraries that you could think of, all of the operating system tools that you might want to, machine learning models, scientific libraries that are huge, anything that you might need inside of your function to operate. In terms of attached storage for a Lambda function, the two main models for being able to store data outside of that function environment and potentially share it across other function executions or other parts of your infrastructure that you might have, Amazon S3 and Amazon EFS, or Elastic File System, File Service, I should say, are still your two options. And so you can mount EFS volumes to Lambda functions. That's something we announced back in the summer months of 2020. And then, S3 support is something that's been with Lambda since the beginning. So nothing has changed about those either. So I mentioned another big announcement that we had at reInvent, which was larger Lambda functions. This is larger in the context of how much memory is available to you, as well as the amount of then CPU that comes proportionally with this. So with Lambda, we used to give you up to 3 gigabytes and 2 cores of memory. Now we give you up to 2 cores of CPU. We now give you up to 10 gigabytes of memory and then up to 6 allocated virtual CPU cores. So as you crank that memory knob higher, you get access to more CPU power. Now, for a lot of you, you will max out your main benefit really at about the as you see here, the 1,769 megabyte mark, just shy of about 1.8 gigabytes of memory, which gives you one vCPU. Because many applications are not multi-threaded, they wouldn't get any benefit from multiple processing cores. And so for most Lambda functions, that is going to give you the most juice that you need for being able to do whatever it is that you might need to do. However, we are seeing a number of customers since this announcement that have started to do threaded or forked processes inside of a Lambda execution. If you're doing any sort of batch processing, maybe if you are doing pulling data from Kinesis or from SQS or DynamoDB streams, this is where we're seeing customers be able to get really interesting benefits from this. So again, more memory equals more CPU, core factor in how Lambda performance operates. You might be surprised to figure out where you are CPU bound versus where you're not, but now you have even more that you can use configured for your Lambda functions. Okay. Lambda Extensions is another feature that we announced back in October of 2020. As the name implies, this allows you to extend the Lambda environment, or essentially get access to other parts of the Lambda environment via what's called a Lambda extension. We've had a number of talks at reInvent that cover Lambda extensions. I would encourage you to check those out, or go read the launch blog or the documentation on it. But essentially, what extensions allow you to do is plug in both third-party tools, or tools you could read or create yourself, into the execution environment. You can do this for security reasons, for operability reasons, for performance tracking, for sharing secrets for things like, say, HashiCorp Vault, or again, putting in log collection tools from companies like Splunk or companies like Datadog or New Relic. There's a bunch of awesome partners that are part of this. So extensions, again, is something we announced before OCI. It does end up working a little bit differently. Previously, with extensions, when we first announced it, you configured them with an AWS layer. Layers do not work with OCI the same way. So what you do need to do is take the code that was in a layer and pull it into your into your container image. Now you can do this via a staged model, so where you basically sandwich multiple container images together, or you could just pull it into your core container image that you build your application in. So we see here a really brief example of how you might want to do that, the things that you would use to pull in inside of a Docker file for this. Similarly, if you have layers in general that you want to import into a container image, this was worked up by one of my peers. And so this is something that you could execute again, as part of a Dockerfile to be able to copy in the relevant information that you need from a Lambda layer. So really pretty straightforward. And we have examples of this in an awesome blog post that was written right after the container image support launch. I'm going to provide a link here at the end that has a link to that post. And then lastly, I would say the last biggest, or one of the biggest announcements that we had from reInvent was a change to how we bill Lambda in terms of the granularity of the billing. So previously, we used to bill Lambda functions at 100 millisecond increments. That has now been decreased all the way down to 1 millisecond. What this means is that customers that had sub 100 millisecond function executions, some of them were saving 70 or 80% off of their Lambda bills for function duration costs. That's a massive savings. For customers even that bill over 100 milliseconds, you're going to end up saving money. And again, it depends. If you were executing a function in 101 milliseconds, you used to have to pay 200. Now you'll pay exactly for 101. So that is one change, again, not related to container image support, but something that has just changed for Lambda. This took effect in the December billing cycle, so you might have missed this change in your billing. Go back and check it out and compare month over month, and you should see the savings pretty clearly. Okay, last thing I'm going to touch on about this is that as part of using, or as part of container image support for Lambda, there is one minor additive change, again, which is that your images have to first be put into Amazon Elastic Container Registry, or ECR. Now, ECR is a service in the container space that's been around now for a couple of years. It has a whole bunch of capabilities. I wanted just to list some of the key ones that I think that are really valuable here. And again, if you've been deploying Lambda functions by copying your code first into S3, you've had some of these capabilities, but really doing this with ECR gives you a number of benefits of official, artifact store, as it were. Again, all the kind of things you'd expect. Really fine-grained IAM permissions that are possible, identity access and management. ECR repositories are private by default. CloudTrail logging applies to repositories and objects inside of them. You have encryption support for at rest and in transport to Lambda. You can do cross-account controls. You can do cross-region replication. And a really cool capability of ECR is that it has integrated vulnerability scanning. This looks at the container image, looks at things like your Docker files, and can identify places where you might have, say, out-of-date packages or dependencies, and make general recommendations on how to improve them. All of how that works is in the ECR documentation, again, which I will include a link to. Okay, so wrapping up, the last thing I want to touch upon is that here at AWS, we love our partners, and we love the people that are in the ecosystem, both the consulting partners and the companies that are ISVs that are building products on top of ours. So in terms of consulting partners, though, and in relation to container image support, the companies that you see listed here on this slide were considered or are considered our launch partners of this function. They've been with us, working with us for the last several months to make sure that this capability is built in the best way, that it's going to meet customer needs. They've been battle testing it with us, and they are ready to help you build serverless applications using container image support or any of the many different capabilities that we have. And so these are the go-to companies that if you said, hey, we need help doing something, we're going to point you in their general direction. So please do check them out if that is something that you're looking for. In closing here, first of all, you can go to this link that you see here on this slide, s12d.com/svs209. This is a landing page specific for my talk that has links to other sessions, other videos, documentation, blog posts, and all sorts of things that you can read to learn more about this. And S12D is a short link service that we run. Or you could scan the QR code that you see here. It'll take you to the same place. Again, container image support, really exciting for what it means to Lambda, what it means for serverless application developers, unlocking new capabilities, simplifying the tooling experience, allowing you to more easily build and manage your dependencies. We think that there's a whole lot of value in here, and we think that we're going to continue to see customers pretty excited about it. That said, we're always looking for your feedback, and so I'd love to hear more about this if you have any questions. My name's Chris Munns. I lead developer advocacy for serverless at AWS. You can find me at munns@amazon.com or at Chris Munns on Twitter. Thank you for joining me today.